Hello everybody, this is Homer White back again with the 10th chapter of our book, 5th part. We're working on tests of significance. In this part, we'll learn about the dangers of limited reporting of your results and also the difficulties associated with the practice of data snooping. Always remember to make sure that the necessary packages are loaded. So we first talk about limited reporting. You wonder if any of your friends possess telekinetic powers. Let's say you have 20 friends and you gather them all together. Let's say that each friend is going to flip a fair coin 100 times, and while flipping that coin, he or she is going to try to make it land heads by concentrating on it. Let's say these are your first 10 results from your first 10 friends. Many of the results are quite near the expected number of heads, 50, if it's just a fair coin being flipped and the person has no ability to influence the outcome. There's a couple of people who got a lot of heads. And your next 10 results, there's a couple of people who also got a goodly number of heads. But your attention is especially drawn to friend number 4 back there, the one who got 61 heads. And you wonder, is friend number 4's performance strong evidence that for her, the coin had more than a 50% chance of coming up heads? So you try a significance test. You let P be the chance that the coin lands heads when friend number 4 is concentrating on it. Now, nobody knows this probability for sure, but you can imagine two hypotheses about it. Null hypothesis is that the probability is 0.50. It's a fair coin, and your friend has no telekinetic powers. The alternative hypothesis is that P is bigger than 0.5, so something's afoot here. Maybe your friend has some limited telekinetic powers. We can use binom test GC to run a test on the situation. We put in the number of successes, 61, the number of trials, 100. The null hypothesis thinks that P is 0.50, and we're doing a one-sided test, a greater than. If you run this test, you find the p-value, the chance of at least 61 heads, given that P is just 0.5, is pretty small. It's 0.0176. So you reject the null hypothesis, and you conclude that there's strong evidence here that friend number 4 has telekinetic powers, at least to some extent. Now there's a fairly obvious problem with this procedure. It's simply that you ignored the data from the other 19 friends, many of whom did not have remarkable results at all. You really need to take all of your data into account, and your p-value should reflect this. Let's think a little bit more about it. Really, the better p-value would be the probability that at least one friend out of your 20 gets 61 heads or more if, all the time, for all the friends, the probability of heads was just 0.5. How might we compute such a probability? There's various ways. But here, let's try some simulation. First of all, you should copy and paste this code into the console. It's going to teach R a new function called headmax. This function has 3 arguments: friends, flips, and coin. Friends is how many friends you have. Flips is how many times each friend is going to flip the coin. And coin is the chance that the coin lands heads. So if it's a fair coin, that's going to be 0.5. And what this function is going to return is the maximum number of heads that any of your friends gets. Once you have taught R that function by running that code, then call the function with the argument friends is 20, flips is 100, and the coin supposedly was a fair coin, and if nobody has telekinetic powers, it remains a fair coin at probability 0.5 of heads. This is going to simulate that entire experiment, and it'll return to you the largest number of heads that anyone got. So what you want to do is run that function. Run it several times, and just see how often is the maximum 61 heads or more. You'll find that it's not so unlikely an event. In fact, the real probability that at least one friend in 20 is going to get at least 61 heads in the experiment of the sort that you had in mind is pretty large. It's about 0.299, about 30%. So from this point of view, the total data that you have on hand from all 20 of the friends provides essentially no evidence of telekinesis. There's a lesson here. It's about limited reporting. If one portion of your data shows an interesting pattern and the rest doesn't, don't just test on the one interesting portion and report only on it. You owe it to your audience to tell them about all of the data that you have collected. After all, when a great many people flip coins 100 times, even if there's nothing interesting going on at all, and all the coins are fair, chances are that someone's going to get an unusually large number of heads, just by chance, and not because of telekinetic powers or the coin being weighted or anything like that. Now let's talk about data snooping. I'll remind you about the attitudes data frame, the large survey that was conducted at Georgetown College in November of 2001. Remember, there were 267 subjects, and they were asked a large number of questions. The primary research questions that we had in mind when we designed the study were three. Does the suggested race of the defendant affect the sentence that is recommended in that hypothetical situation about the person convicted of killing someone while driving drunk? Also, connected with that question, does the suggested race of victim affect the sentence recommended? And then, in connection with the question about the rock concert, does the way one lost one's money in the hypothetical scenarios surrounding attendance at that concert affect the decision about whether to attend the concert anyway? Those were our primary research questions. But the data frame has a lot of variables. And when you look at all those variables, then a lot of other research questions just naturally suggest themselves to you. So we might play around with a few of them. So we've got the variable sentence that says the recommended sentence that each respondent gave to the defendant who was convicted of the involuntary manslaughter. We also have the sex of each survey participant recorded. So you might wonder, who's harder on crime? Who tends to give longer sentences, a Georgetown College female or a Georgetown College male? Well, we know how to study questions about the relationship between a numerical variable and a factor variable by now. We can do it with favestats, numerical variable sentence, broken down by the values of the factor variable sex, using the attitudes data frame. And when we take a look at the results, we see on average there's not much difference between the sentences recommended by the females and those by the males. There's not even a 2 years difference between the sample means. So there's probably not much interesting going on here. Let's turn to another question. Who's more likely to decide to attend the rock concert? A female or a male? This time we're thinking about the relationship between two factor variables. One is the explanatory variable, sex, and the response variable here is the variable concert decision, yes or no, whether you decide to buy that ticket anyway. And we can study those kinds of questions with X tabs. And with formula data input, it's twiddles, explanatory variable plus response variable, and the name of your data frame. And we've got some row percents to nail it down. And what we find is that about 67% of the females in the study would buy a ticket in their situation. And about 62% of the males in the study would buy a ticket in their situation. Now that's about a 5% difference. But there's only about 150 at most of each of these sexes involved in the study. And a 5% difference based on such a small sample size probably isn't so terribly interesting. So there's probably not much going on here either. Let's try another research question. Who's harder on crime? A Georgetown College student who would decide to attend the rock concert, or a Georgetown College student who would decide not to attend? We're looking here at the relationship between the numerical variable sentence and the variable concert decision, whether or not a person would, in the hypothetical scenario, decide to buy that ticket anyway. So applying favestats, we see the results are that the average sentence handed down by folks who said they would buy a ticket was about 28 years. And the average sentence handed down by folks who said they would not buy a ticket in that situation was about 24 years. That's more than a 4-year difference we're looking at here. This might be interesting. We can look at it graphically too. So here's a density plot of the people who said that they would not buy a ticket. Notice it's tall towards some of the lower sentences in the 10 to 20 year range. Here's the density plot of the people who said they would buy a ticket. It's not so tall in the 10 to 20 year range, but it's quite tall around 50 years. I bet a bunch of people who were in the buy group were handing down the maximum sentence or close to it. This looks kind of interesting, especially in conjunction with that over 4-year difference in the averages. We should take a closer look. Let's run a test. So let's state our parameters. Let's let mu1 be the mean sentence recommended by all Georgetown College students who would buy a ticket to the rock concert. And let's let mean 2 be the mean sentence recommended by all Georgetown College students who would not buy a ticket to the rock concert. We're going to test whether the difference in the means is 0 or whether it's not 0. Two-sided test. So the code's pretty straightforward. We're going to use t-test GC. Sentence twiddles concert decision. Data is attitudes. Null hypothesis thinks that mu1 minus mu2 is 0. And we're doing a two-sided test, so we don't have to say that the alternative is two-sided. That's the default value. And since we defined the buy group as the first population, let's make sure that the function recognizes this. And we'll do this by specifying the argument first to be the value buy. Here are some of the results. The test statistic turned out to be 2.172. So our results are more than 2 standard errors above what the null was expecting. The p-value is only about 0.03. That's less than our usual cutoff, 0.05. So we're going to reject the null hypothesis this time and conclude that this data provides strong evidence that Georgetown College students who are inclined to spend money on rock concerts are harder on crime than those who are not so inclined to spend that money. But there's a problem here too. It's not like we are intentionally ignoring data or hiding data from our audience. It's just that we did not plan in advance of collecting the data to perform this particular test. We decided to perform this t-test based upon an interesting pattern that we noticed in the data after we'd collected it and started pawing through it. That's data snooping. Data snooping is the practice of performing an inferential procedure on data based upon a pattern that you observed in it. So you decide to do a certain test because you saw a pattern that suggested that you should look into that test. Now, I'm not saying it's bad to do these tests or to look around in the data. Curiosity is a very good thing. But if you look at the data from many points of view and then perform inferential procedures on those angles that look interesting or promising, then you're liable to conclude statistical significance when there was only chance variation. More technically, the real probability of committing type 1 errors, when nothing's really going on, is higher than that nominal probability given by your alpha cutoff level. And frankly, humans are very good at detecting patterns. For every pattern that we notice in data, there's probably thousands that we would have noticed had they been present in the data. When we look at data, when we see a pattern, rest assured, there's a great many other patterns not there at the moment that we would have noticed and been interested by had they been there. We're not even aware of all those patterns that aren't there. They don't come to our attention. But what's really going on when we look at a thing and examine it is that our minds are checking for all different types of patterns, and we're only being alerted to those patterns that are there. So in reality, we are looking at data from very many points of view, so many points of view that we have no idea what they all are, no conscious idea. So what should we do? We should not shut down our curiosity. And performing tests are a crucial thing. They help us to tell the difference between just chance variation and what might be a real pattern out there. So we suggest that if you do go ahead and perform tests based on patterns that you notice in data, that you distinguish between primary research questions, questions that you decided upon in advance of collecting data, and secondary research questions, ones that occurred to you after you looked at the data and saw an interesting pattern. With primary research questions, you plan to perform a test regardless of what the data looks like. With secondary research questions, the decision to perform the test came later and was based upon a pattern that you noticed and perhaps did not expect when you first gathered the data. The general guideline is that conclusions for those secondary research questions, the ones where the tests are performed and so show some statistical significance, conclusions for those secondary research questions should be cast as very provisional indeed. You should portray them to your audience as more of an invitation for them to investigate further, perhaps with new data that they collect, rather than as definitive, once and for all, conclusions about the way things are in the world. Thank you for listening.